One-to-one functions and inverse functions, Chapter 5, Section 2. A function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. That is, if x sub 1 and x sub 2 are two different inputs of a function f, then f is one-to-one if f of x sub 1 is not equal to f of x sub 2. Now, if you remember with a function, we said any input has to have exactly one possible output. But any output could have multiple inputs. So basically, if I gave you a value of x, you had to be able to tell me with 100% certainty what y was. But if I gave you a value y, you didn't necessarily have to tell me what x was. Remember, I gave an example of first names and last names. Now, if I only have one Michael in the class and his last name is Jones, since I have only one Michael and I say Michael, we know that I'm referring to Michael Jones. So if that's the case for all of those, that any first name has only one last name associated with it, we have a function. It's okay if I have one Chris in the class and his last name is also Jones, because if I say Chris, we know that we're referring to Chris Jones. So that's a basic function. When you're dealing with one-to-one, we're saying it has to go the other direction, that I can only have one of each last name in the class also. So if I have Michael Jones and Chris Jones, I do not have a one-to-one function because I have two different x values that give me the same y value. So I'd have to have Michael Jones and Chris Smith. Then I'm okay, because given a last name, I can now tell who I'm referring to. If I say Mr. Jones, Michael responds. If I say Mr. Smith, Chris responds. So one-to-one function just means now for every input, there is only one output, and for every output, there is only one input. Now, if you remember, when learning about functions to begin with, we said they had to pass the vertical line test. So if you drew a vertical line anywhere on the graph, it would only touch the function at most one point. Well, since now we're one-to-one, we're saying that the things work in reverse, that there can only be one input for every possible output also. Then we can add the horizontal line test, which says if every horizontal line intersects the graph of a function f and at most one point, then f is one-to-one. And the reason we can say it's just a horizontal line test is because we are already stating that it's a function f, which means it already passes the vertical line test. So if I take this given function and look at that, I go, okay, well, I know it's a function. Well, let's see if it's a one-to-one function, and we take a horizontal line and we can move that horizontal line up and down, and it's only going to cross that graph at most one point. So that's a one-to-one function. This also is a function, but we see that if I try the horizontal line test, it crosses over the function twice, which means that it is not one-to-one. So let's get into a theorem here. A function that is increasing on an interval I is a one-to-one function on I. So if the function for its whole time period in that interval is increasing, then it must be one-to-one. In a similar light, a function that is decreasing on an interval I is a one-to-one function on I. So again, if it's decreasing over the whole interval, then it has to be a one-to-one function. A lot of words on this page. Inverse function of f. Suppose that f is a one-to-one function. Then corresponding to each x in the domain of f, there's exactly one y in the range because f is a function. And corresponding to each y in the range of f, there's exactly one x in the domain because f is a one-to-one function. The correspondence from the range of f back to the domain of f is called the inverse function of f. The symbol f to the negative 1 is used to denote the inverse function of f. So all that's saying is that if you have a function f, then its inverse function basically swaps x and y. Your inputs become your outputs become your inputs. That's all that verbiage is telling us. So if I gave you a list of ordered pairs and said, find the inverse, you would just swap x and y for each of those ordered pairs, and then you would be giving me the inverse of the function. Domain and range. The domain of f is equal to the range of the inverse of f. Also, the range of f is equal to the domain of the inverse of f. And that's what I just said. You're going to swap your x's and y's. Whatever was x becomes y, whatever was y becomes x. Composition of function in inverse. The inverse of f of x is equal to x, where x is in the domain of f. So if you take the composite of the inverse composed of the function, you get x. F of the inverse of f of x is equal to x, where x is in the domain of the inverse of f. So if you take the composition of f composed of the inverse of f of x, you get x. Which should make sense, because what is that really saying? It's saying if you have a function and its inverse and you plug the one into the other, it should undo whatever it's doing. And that's what an inverse function really does. It undoes the original function. So if I have a function that changes 3 into 7, the inverse function will change 7 back into 3. Kind of think of it as an encoder and a decoder. Think of when you used to take the alphabet and turn it into numbers to write an encoded message. And if you had A equal to 1, B equal to 2, C equal to 3, right? You had all these, you just had these, that was your encoding. So you took whatever the letter was, and you wrote down its corresponding number. And then to decode that message, you did the reverse of that. You looked at whatever the number was, and you found its corresponding letter. That's really what the function and the inverse are doing. The function takes an input and turns it into an output. The inverse then takes that output and turns it back into the input. We sometimes refer to things like this as opposite operations. Squaring is the opposite of taking the square root. Division is the opposite of multiplication. So those are a function and their inverse, or a relation and its inverse. So let's determine if two functions are inverses. Well, given f of x is equal to the square root of x minus 3, and g of x is equal to x squared plus 3, we want to know if these two functions are inverses. What we're going to do is we're going to take the composition of those two functions. So f of g of x is equal to the square root of x squared plus 3 minus 3, which I don't want to be the one who has to break that down into pieces, but we'll just say that that's not equal to x. That 3 and negative 3 can't cancel each other out. So that composition is not equal to x. Well, let's check the other way. G of f of x is equal to the square root of x minus 3, the quantity squared, plus 3, is equal to x squared minus 6 times the square root of x plus 9, which is also not equal to x. So since the compositions were not equal to x, they are not inverses. Time for another theorem. The graph of a one-to-one function f and the graph of its inverse function f to the negative 1 are symmetric with respect to the line y equals x. Now remember, when we talk about these, how we get from a function to its inverse or vice versa is just by swapping x and y. So it makes sense that the graph of the function and the graph of its inverse would just be symmetric or reflected over, the one reflected over the line y equal to x. So let's look at an example of this. We have f of x is equal to x cubed minus 2, and the inverse of f of x is equal to the cubed root of x plus 2. So here I have a graph of x cubed minus 2, and we know what x cubed looks like. We know that this is just shifted down by 2, and you can see that that's what happened there. I'm now going to put the line y equal to x so that we can reflect x cubed minus 2 over that. So if you look at that, you see, well, when x is equal to 0, y is equal to negative 2. So if we take the inverse of that, when x is equal to negative 2, y should be equal to 0, right? Just swapping x and y. So if we plot the cubed root of x plus 2, we get the following, and we see that what was the y-intercept of f of x is now the x-intercept of the inverse of f of x. What was the x-intercept of f of x is now the y-intercept of the inverse of f of x. And we can see that they cross the line y equals x at the same point, right? And you can look at and you can see that it's just a mirror image over the line y equals x. So if I gave you a graph of a function and said find its inverse, all you need to do is draw the line y equal to x and then reflect over that line. Speaking of finding the inverse of a one-to-one function, that's fine if you're graphing, but what if it's given to you algebraically? In y equals f of x, in y equals f of x, interchange the variables x and y to obtain x equal to f of y. This equation defines the inverse function, inverse of f, implicitly. If possible, solve the implicit equation for y in terms of x to obtain the explicit form of the inverse of f, y equals the inverse of f of x. And then check the result by showing that the composite functions, inverse f of x is equal to x, and f of the inverse of f of x is equal to x. Now, when we're talking implicit versus explicit, remember that we talked about implicit functions and explicit functions, that implicit functions were ones where there was a relationship, but it wasn't set up telling you that y is actually equal to something. You just have x and y in the equation somewhere. Whereas the explicit form was where you solved for y and said y is equal to, and you showed a function that dealt with x only. So we want to find the inverse of f of x is equal to 3 over x plus 2. So the first thing we're going to do is we're going to call f of x y. So y is equal to 3 over x plus 2. We're then going to swap x and y. So x is equal to 3 over y plus 2. Now we're going to start solving for y. So the first thing I'm going to do is I'm going to multiply both sides by y plus 2. So I get y plus 2 times x is equal to 3. I'm trying to get y by itself, so I'm going to divide both sides by x. So I get y plus 2 is equal to 3 over x. And then again, I'm trying to get y by itself, so I'm going to subtract 2 from both sides. So y is equal to 3 over x minus 2. And then the final step is just to now say, okay, this is the inverse function. So the inverse function f of x is equal to 3 over x minus 2. Now we're not quite done yet because yes, we found the inverse, but now we need to look at the domain and range of these. So if I'm looking at f of x is equal to 3 over x plus 2, I can see that domain is going to be x not equal to negative 2 because we can't let the denominator be equal to 0. The range is going to be equal to 0. Well, wait a second. How did you see that, Mr. Davis? Well, remember that we said that the domain of the function is equal to the range of its inverse, and the range of the function is equal to the domain of the inverse. So I took the quick, easy step and I looked at our inverse function, 3 over x minus 2, and said, well, x can't be equal to 0. So essentially, I found the domain of the inverse of f of x to be x not equal to 0, and therefore the range of the inverse of f of x, y can't be allowed to be equal to negative 2 because that was the domain of f of x. So we can see that we can use the inverse function to give us the range of the original function. So if we know the domain and range of the function, we now know the domain and range of the inverse function because they just swap places. And if we know the domain and range of the inverse function, we now know the domain and range of the original function. Or if we know the domain of the function and its inverse, then we know the range of the function and its inverse. So pretty handy to know. So that's dealing with inverse functions and one-to-one functions.